Space weather. 1995, roughly, someone thought up the term space weather to describe what I thought I'd been doing for the last 20 years of my life. And I have to say that I feel that as a participant in history, I can't remember the history of this subject terribly well. It's, on many of us, I guess, have that experience of being part of history, but feel we're left behind somewhere. So, in this particular talk, I wasn't quite sure what would go down or what would be most interesting to you people. And space weather is a very large subject. I'm going to talk a little bit about what space weather is and its impact, and who's doing something about it, and then maybe some little digressions. The space weather environment that I understood was really the little bit of this portion up here. Just there. Space weather was in there. So in 1995, we've now expanded our horizons right out to the edge of the heliosphere. And we have interesting things coming in here, and people even regard what's coming in through the heliosphere from the outer galaxy as affecting our weather and our environment. I won't talk about that. I'll stick with the sun. This is the seat of all space weather. That's the Earth sitting in the middle of a sunspot to give you a feel of the scale of these objects we look at. And to remind us some of the history, this is a picture that Galileo drew of the sunspots on the sun. And on some websites, in fact, I should have shown you the movie to prove that Galileo could have made the first movie of sunspots. The solar terrestrial environment, or the space weather environment as we call it now, starts at the sun with a variety of activity here, impinges on the Earth, follows the Earth's magnetic field around it. That magnetic field contains particles. As the sun changes, it changes the solar wind. That change reaches the Earth, compresses the magnetic field, alters the particle populations, and causes a variety of problems. That's what we call space weather. The other way of looking at weather is that it doesn't affect us, it's climate. If it affects us, it's weather. And that's what we're most interested in. That near environment, of course, this is the interface of the space environment, the sun's atmosphere, if you like, and the Earth, called magnetosphere. Everything must pass through the magnetosphere in some fashion. If you like complicated physics, you can do it in the magnetosphere. I'll try and keep it where I can understand it at least. So we have the progression of events. We have an event on the sun. This is a scene captured by various space cameras. We go through to see something in goes. This is the electromagnetic event. It's followed by a particle event a short time later, and that blinds our sensors. Our spacecraft are also experiencing this if they're out at L1 in a more hostile environment, the sun's atmosphere. Here's our X-ray event. It's very important if you're an HF communicator. You people in space environments, of course, HF communications is not quite your field, but over-horizon radars and aircraft all use still HF in some fashion. These particles or the space environment issue. So, what is this impact? We can think of very simple pictures. We have our electromagnetic effect comes immediate, and we have a variety of effects that has. Later on particle events, proton events, and that has a series of effects on the spacecraft and the space environment. And following on that, we have what we call a coronal mass ejection, CME, and that's the changes the entire magnetospheric environment and impacts down to the level of the Earth. And the way in which this takes place is we have the ionosphere. I have to say my life has resided in the bottom side of the ionosphere primarily. And currents can flow in the ionosphere. It's a conducting medium. It's a very light placement, but the currents can flow there. As currents flow, they produce magnetic field effects at ground level. If you have long conductors like a pipeline or a cable or power lines, then you can induce a current in those, and that current can be detrimental. And then we can go around, there's a variety of things, geomagnetic prospecting, radio, and or GPS. All of these can be impacted by the changes in the space environment. So this is the main area that, say, I work in and have customers in. Spacecraft also have their own problems, and I'll mention that in a moment. So we can identify all these problems, but maybe it's colour code them. You know, green's good news, red's bad news, red's hard to read from the back, no doubt, and who wants to hear about problems anyway? But we'll find this new atmosphere. There's a number of good things about it, but it damages some things. We have interference that can propagate. Archaeological studies even can be impacted by this. They're outreach of geomagnetic prospecting. Power distribution problems. Micrometeoroids and space debris all sort of captured under the space weather banner in our eyes. And up here we've got magnetic problems, atmosphere. Atmospheric drag is very important for removing debris these days. Everyone has to figure out how to get rid of the stuff that's seen up there, I understand. So that changes, and we move down through a whole lot of other problems. So I mentioned aurora at the bottom. We have a lot of people who are very interested to see an aurora. So that's a particularly nice part of life. We have many customers then. We can group them by types, or we can group them by agencies. There's different types here, in general, different groups, government bodies, private bodies. So if we move into space, we have what we call our space-based assets. This is a French term, actually. I heard particularly like it. And anyway, up in space, there's two functions. Your spacecraft is in a hostile environment, and it wants to put information back down to the Earth. And the information channel is going to be impacted by the space environment also. The space environment for the aircraft is somewhat akin to an atomic bomb. It's an unfriendly environment. If we think in terms of the magnetosphere, as I mentioned before, you have sort of typically a geo orbit, the GPS Galileo, and your international space stations in here. So the colour-coded bits, their particle energies are higher than quiet, if you like, and these fellows on the space station are quite sensibly below that environment. They have cosmic rays to over that, of course. The spacecraft, sitting out in these environments, has a range of problems that it can suffer from. I won't go through all those. I'm sure that you people are well aware of that, as my next slide shows. And this goes through all these aspects of space weather. That the people who are affected by space weather do know they are affected. They don't cast a blind eye on it. And they have some risk management process in mind as to cope for it. So with a spacecraft, engineers typically design them to work in unfriendly environments, and we understand that. Now, this point's usually lost when you hear you've heard space weather, you've heard of 2012 is the end of the world. Civilization as we know it will finish because of major events on the sun which will occur. I'll come to that later on and explain where that little myth comes from. But the same type of myth is told about everything about space weather. The main driver of this, of course, is funding. If it's a dangerous problem, then funding can be attracted by a dangerous problem. But it's not so much a dangerous problem if we do something about it. But it is a dangerous problem if we ignore it. Nevertheless, we can have extreme events we're not expecting. I've mentioned two down here. And spacecraft were lost, and GPS outage, 6th of December. The 8 spacecraft were lost at the time when there was spikes in the electron concentrations. This was just a normal storm feature. The spacecraft evidently wasn't designed to deal with that situation, or else they thought it was an unlikely event. The GPS outage, you'd have to say this is a very unlikely event. In fact, it's qualified as probably a 1 in 30-year event. I think that's worked out because we had about 50 years of data and it happened once. And so on a statistical basis, that means it's about 1 in 30 years. If we take that portion there, we can expand that up and see more clearly what we're seeing. What we're looking at, the coloured area here is the emissions we're seeing from radio emissions. And that radio burst was occurring in the frequency range we were monitoring very closely. You'll notice how it truncates very clearly. It's not a saturation effect by any means. It's a software switch that was put in and said, radiation will never reach this level. In fact, it's going to be a few orders of magnitude low, so at least not follow. They were quite capable of measuring much higher up than this, but unfortunately the software switch stayed in place and we've missed a unique event, maybe, or maybe the type of event we have to think about in the future as being more common I'll explain why that comment's made. So this just then shows you how the GPS satellite's tracking through, and it gives you a feel for how their signal strengths are changing. And if you look at the upper panels, you can see here the GPS signal is lost completely. Well, that's not a big surprise in Antarctica. You're a bit short on signal there, but it so happened we had one of our people who had taken a GPS receiver to Antarctica, and on this particular moment decided to try it out and got no reception and thought, well, that's it, GPS doesn't work down here. So it was an unusual accident, and he came back and produced this picture afterwards. So if we look in the space environment, the red areas tell us these are important. We have different levels, different types of satellites, we like different orbital heights. And the red tells us there's things we would like to watch out for, things we pay attention to, basically things the engineers taken into account when they were looking at designing that particular spacecraft. And I've got a couple of tables there that I won't spend time on. I'm not too sure whether everyone gets hold of these presentations after the event, but if you do, you can have a look through those. And well, they're just summarising some of the things in the space environment and within the context of space weather that are useful to know about. We go on to the signal. It passes through the ionosphere, and as it passes through the ionisation, irregularities within the ionosphere impose small phase and amplitude variations on that signal. When they're summed up at the ground, the signal is no longer a pure signal. It has a sort of a movement to it. It scintillates. And basically you must deal with that scintillation. One way is to transmit sufficient power so you are well outside of the range of scintillation. There are regions within the tropics where that scintillation, particularly in the post-sunset period, can be particularly severe, and so you need to be aware of that climatology, and maybe in some cases pay attention to it. Depends a little on frequency. Basically, climatology and predictions is how you set up your suitable margins. Nowcasting and forecasting for your anticipating the worst case, and technology is also your friend. You need to use robust equipment. If you go to GPS, different levels of GPS respond differently to the environment they're working in. A rather expensive defence-oriented GPS system, much less likely to fail than the system that most people would use. Most people are not so worried about the levels of accuracy, but then if you're landing a plane, you'd like to think they've got a fairly good GPS system involved. This is GPS in a scintillating environment, and you can see what happens is you've got these signals coming down to the aircraft, but they pass through this region with a loss of tracking. The aircraft is a ranging error. They're not exactly sure where they are, but of course they have a lot of information. Besides, I said, anyone who's involved in this is aware of the problems they can experience, so they make allowances for that. But nevertheless, these act as a boundary, if you like, in how you operate. And you must be aware of the boundary and manage it successfully. So we have our signal coming down with a signal envelope there to fuel some modulation. You can look at the bulk change that occurs through the ionosphere, and you can model this. This is something we do and a number of other groups in the world do. Instantaneous picture here. This S4 index is an index that gives you a picture of how much scintillation is occurring, and it's the little patch here sitting. It doesn't deliberately sit off Australia all the time. It just happens that picture was chosen, so it was focused on Australia. This is, I've forgotten what time it is, 12 UT. I can paint a synthetic picture here. This is actually what we call just builds, and so you can see what that region looks like all around the world. You've got these two bands sitting near the equatorial anomalies, we call it, and those regions where we get the bulk of our scintillation. We go to the thermosphere. Now, if you remember, we showed a picture of the Earth. This is now in the near Earth, and this is the sorts of activity that's going on. You don't need to know all those things that are going on there. That picture's probably one we would have liked to have painted 20 years ago, or wouldn't have felt quite so confident about as we do now. This is the environment of the space drag, basically. This is the thing that heats up the thermosphere and alters it over the solar cycle. The thermosphere becomes warmer, hotter, and drag increases. We go to solar limit, it's cooler, less drag, and these are the types of forces that are acting on it to alter that. When there was a major storm, March 1989, what we've got here is the envelope of the storm, and plotted across here is lost satellites. Someone's keeping track of all the bits and pieces of things that are in space, and during a storm we heat the thermosphere up, and that heating up changes the orbits, and for a period of time you've lost satellites and you have to regain them. Really this emphasises that the medium is impacting the spacecraft all the time and keeps the tracking person on their toes, if you like, in this particular instance. Cosmic rays, I mentioned previously, just briefly, there's one part of the spacecraft environment. There's certainly the manned space environment. And cosmic ray flux varies with solar cycle, so that as you move towards solar minimum, you have a maximum in cosmic rays. And during this recent solar minimum, we've had our largest fluxes of cosmic rays observed in the space age. And that's because this has been the longest and deepest solar minimum of the space age. And so we've got a picture here. This gives you a picture of magnetic activity. This is the sunspot number, which is the sunspot number that drives a cyclic variation of space weather. It's a 11-year cycle. And up the top here, we've got ground effects, ionospheric effects, and space effects. Now, that doesn't mean that ionospheric effects didn't occur before 1920. It means we didn't know anything about them much before that point. This gives you a feel of where our technology noticed the space environment affecting it. So this up here is telegraphy. And the telegraphers, back in the late 1800s, they have reports in their local newspapers that the telegraphy was driven by currents of unknown origin, admittedly caused by the aurora, correctly. And so we have space weather affecting that technology. The break here is sort of feeling that, we lost track of that for a little while. And if we move out further, we've got the space effects. Well, space effects occurred when we got something in space to experience them. That's really the heart of space weather. Space weather affects our technology. And so as our technology becomes more complicated, covers wider range, it becomes more sensitive, it starts to become more sensitive to space weather effects. So that's just little reminders of that. And so who's doing something about that? One of the first groups combined internationally was what we call IUWDS, International Oceanography and World Day Services. I have to look at it to remember it these days, but it used to be very familiar to us back in those days. This morphed itself into the International Space Environment Services, which was one of those name changes that really does give meaning to the organisation. It's a group, it doesn't encompass every country of the world by any means. It encompasses several countries, have their what they call a space forecast centre, and this community tries to participate together and exchange data and understand collectively what the sun is doing to our environment, our space environment. IPS is one of the members of that group. We were founded in 1947, and we now have a network which spans, or we have access to data with a network that spans our local region. And other groups have very similar networks, maybe not exactly like our one, but to meet their needs. World Meteor Organisation has developed an interest. Their interest is driven by this turning into this constellation of spacecraft which drive their weather forecasting. And they're vulnerable if their spacecraft are vulnerable. So they are now very interested in space weather, not so much for their vulnerability. They're starting to see that the way in which space weather is being handled internationally is, if we go back to that picture, only a small community of people passing this around in the region. The WMO feel this is not adequate. Actually, I think they use the word amateur. We accept the criticism, and we're happy to participate with WMO to broaden the scope of what we do. We have a little group forming here, the Asia Oceania Space Weather Alliance. The first meeting will be next week, actually, in Bandung, Indonesia. And we know Japan, Indonesia, Australia, I believe Malaysia will have people. We have 2 people attending. This is very much helped ahead by the Japanese, who will be funding much of this activity. And this is something which we look forward to as a growing group within our region to handle space weather between our different communities. And another group, International Living with a Star, is a group that comes out of NASA and embraces other space agencies and helps to coordinate the type of observations we're making to understand what space weather is doing. And this gives a timeline of some of the sort of proposed and current spacecraft that provide environments as well. We're very good at telling you what's happening right now. We're very poor at telling you what's happening about 12 hours in the future and 24 hours in the future. Persistence forecasting still beats us because we're so clever. We're down to try and beat persistence forecasting. This gives you a picture. Well, notice the green X-ray fluxes, courtesy of the various spacecraft at Citadel-1. And that's very valuable information. That's something I would have loved to have when I was a forecaster back in the 80s. I'd have to say that forecasters don't know how well off they are, because I was forecasting with nothing. A magnetic field and a glimpse of the ionosphere is all we used to have, and a picture which was 24 hours old of the sun. This is much different, but we still don't do our job as well as we'd like to. It's a very difficult problem to solve. It's a magnetohydrodynamic problem. We're pulling the energy through the magnetosphere, projecting it across the Earth, and it's a major problem yet to solve. We have insights into it. Our solar cycle, as I mentioned before, we had our longest solar cycle. Here, this kind of captures the space forecasting environment very nicely. This is a picture of all of the sunspot cycle predictions for this cycle 24. So we've had estimates up to around 200 and down as low as 40. Who's going to be right? This picture here shows that's the very first spot we saw of what we would call cycle 24. And if we go back a couple of pictures there, you'll see solar minimum is occurring somewhere around about in there. So the first spots of the new cycle become visible before the last spots of the old cycle finally disappear. So that's where we've moved to now. And at the moment, what we've got here is just a little stack plot. It's an awful picture to look at, but our current position in the solar cycle is around there. And if we look at past cycles, it's starting to look a lot like we'll have a cycle like this. So that's my prediction. We're going to have a very low solar cycle. And what does a low solar cycle mean? It tells us a lot of things. Things in green, kind of good news. So for the sun, we're going to have less activity, less regions, because there's less sunspots, because that number is a sunspot number. So that means possibly we'll get fewer flares, and that means we'll have a less shocked solar wind, but maybe not, because we may find we have, and we do seem to find more coronal holes. Coronal hole activity is stronger than what's been the case previously. So that may affect the solar wind a bit unexpectedly, and that's what we're saying over here. Maybe the high-speed solar wind is going to be different. Galactic fluxes increase, although we're moving back to more normal levels now because we've lifted up a little bit there. Maybe fewer substorms. Substorms are sort of important because they power the inner magnetosphere, they energize things and give us problems. And so on. Everything affects all of these different. But I'm going to come just to the last picture here. And this is curiosity that we find during lower solar activity cycles, there's a tendency to get more very big disturbances. And that's the origin of this 2012 doom and gloom story. The suggestion being that our next solar cycle will peak near 2012. It'll be a low cycle. I believe it will be more close to 50 than 70. But it may be accompanied by some very big disturbances. Big meaning, bigger than what we've been familiar with in the space age, but certainly not killer storms. And everyone who's aware of this and doing their job is paying attention to the potential of that disturbance. So while our forecasting is not terrific, our warnings aren't bad. We'll recognise the region that's coming around onto the face of the sun, and we'll know to warn people, and everyone who's doing some work in the space environment will be aware of it. Meanwhile, what's this got to do with this group here? Well, space weather is part of the space environment, and if we're going to utilise space, this is one of the areas we can utilise, if you like, and we can. Those space weather warnings are important to society, and a better understanding of what our space environment is doing enables us to do this job better. Thank you.
Thank you very much. I just wanted to let everyone know before we go to questions that we are aiming to match the scheduled break time at 3 o'clock or shortly thereafter. So I'd like to just limit discussion now to 1 or 2 quick questions. And you can follow up with Dr. Wilkinson in the break as well. So there's a question.
Thank you. The main effect of the space weather is the satellite operational, and also the technology that affected by ionosphere and geomagnetic. You did not mention concerning the effect on the power grid. What your opinion, the effect of the geomagnetic induced current that affect the high altitude power grids, especially in case of the Australia, that maybe there is the long range the power grid system. Thank you.
The problem in Australia it increases when you connect the Tasmanian grid in with the mainland Australian grid. Then you've got a long conductor, and while you would expect this to be a high latitude effect, Australia is actually quite high latitude. Surprisingly so, when the fields, the magnetic pole and the geographic pole are displaced significantly in our sector, and that means that Australia is a little vulnerable down when you get to southern Australia. That's why we can see aurora at relatively high or low geographic latitudes. So that gives you the signal of the warning. If you disconnect Tasmania from the Australian grid at the moment, we think that makes us less vulnerable, but that's easier said than done. And that's actually something that's being discussed. So it's a good question. The power grid in Australia could be vulnerable. That's something we've been looking at this year. And the people who are concerned with the implications of that to the power grid are well aware of the possibilities and are considering what they would need to do to mitigate those effects.
Thank you very much, Phil.
I'm not familiar with the space weather, but I'm interested in using the GPS L1 wave propagation for monitoring the ionosphere activities. So as you may know, the JAXA launched the QGS satellite, which is the satellite navigation. The moving speed of the satellite of the GPS is much faster than the QGS. QGS are something like the point, the propagation from something pointing to the Earth. So, how do you think about such L1 propagation data from the QGS can provide any other additional or variable data for the monitoring the ionosphere activities or not?
I assume that someone with more knowledge of the problem solves it. That's my easy way out of this question. It's not the sort of question that I would deal with myself. But if you're dealing with something coming from L1, there's a time delay, and you need to account for that. And to be honest, it's something as a forecaster I would be less concerned by these days, because I not only have that information from L1, I have a lot of magnetometer stations, and I can monitor the first signs of the solar wind impact of L1, and then 10-20 minutes later I'll see the geomagnetic effect. So I'll get that confirmation that I've got the timing right. And that sort of information's quite soon enough for most purposes. Now, if I'm a power person and I'm concerned, the first thing I see is something happening at L1, which is a significant event, I'll be taking action straight away. 20 minutes to 10 minutes the planet's involved there is nothing. They like that sort of order. So I'm not sure I've answered your question exactly because you're mentioning GPS, but I couldn't quite catch the essence of that question.
Thank you very much.
Okay.